Hello, welcome to my pipeline integrity video series. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today's topic is going to be derivation of the EGAD. Now you're probably wondering what the EGAD is. Some of you have probably seen some of my other videos where I look at development of a model that I've called the gamma exponent model. Well, in this case, the EGAD is the exponential gamma assessment diagram. So what I'm going to be talking about is the derivation of the exponential gamma assessment diagram for axial surface cracks. Essentially what I'm doing here is I'm using my gamma exponent model, which hopefully some of you have seen before, and I'm going through the mathematical exercise of turning it into a failure assessment diagram type approach. Some of you will be familiar with the failure assessment diagrams from industry standards such as API 579 or possibly British Standard 7910. Those of you that are familiar with fracture mechanics may know that the original failure assessment diagrams were derived from the original log secant model. And if you've seen any of my videos involving my gamma exponent model, the GEM, you'll see that it's got a lot of mathematical similarities to those, to the original log secant model. So it seemed to me it was mathematically and theoretically reasonable to see if I could take the GEM and turn it into a failure assessment diagram type approach. Now, this will be particular interest for some of you that rather than doing one calculation, you prefer to do two calculations, one based on fracture, one based on flow, and it'll be particular interest for those of you that enjoy using numerical methods to solve for failure strengths. So for those of you that aren't familiar, this is my gamma exponent model, which I've nicknamed the GEM. You'll see that it's in a very similar format to the original log secant model that was developed by the Battelle Institute back in the late 1960s and early 1970s by the NG18 committee. So starting from the left, we have S fail over S flow. That's the predicted failure strength divided by the flow strength, or some of you will know that ratio as the remaining strength. And then we have 1 minus A over T to the gamma exponent. So 1 minus A over T is essentially our remaining ligament. We have 2 over pi, arc cos exponential, k squared mat is, that's going to be our toughness. We have a 10 factor in there. A is our crack depth, and S flow, again, we have the flow strength in there. Now, you'll see that for a crack-like flaw, the gamma exponent is defined as the crack length divided by the pipeline radius, but up to a maximum of 1. Now, I do have some other videos that I kind of walk through the validation work behind this, and I tell you various bits and pieces of fine print. I don't want to bore you too much, so I'm just going to jump through the fine print. And if you're interested in that, if you've never seen the GEM before and are curious how it can be used, you can certainly stop the video and take a look at the fine print. So here's my first page of fine print. If you want to take a look at it, please stop the video. And here's even more fine print. So stop if you need to, but I'm just going to plow on ahead, hoping that some of you have seen this before. So if I take my gamma exponent model, what I showed you before, I call that the unfolded format. So what I've done here is I've taken that GEM and I've repackaged it. So I've repackaged it in what I call the folded up format. And this is going to look quite familiar to some of you, those of you that are familiar with the original log secant models that were used either for through wall cracks or for surface breaking cracks. There are a couple of key differences though. On the left side, I'm using the 10 factor and the crack depth. In some of the equations you've seen before, there would be an 8 factor and the crack length. And then if you look over on the right-hand side, rather than having the Folius factor buried in there, I have the T over T minus A all to the gamma exponent. So if you think about it, that T over T minus A, that's actually the inverse of the remaining ligament. And that's how the GEM plays out because of the various mathematics behind my derivation. Now, because the original failure assessment diagram was derived from the original log secant model, I've decided to follow exactly the same approach that the original work did, but with a few little twists and turns along the way to accommodate the GEM model. So the first thing I have to do is I have to define what I'll call Kg and Sg. You will know these as the K ratio or the flow strength ratio. And these are going to be the y and x axes of our failure assessment diagram. Now, if you look at the kg here, I've used the g subscript to define it as the gamma exponent version of this ratio. We have 1.12, which represents an edge crack. We have the failure strength. We have the typical square root of pi times the crack depth. And then you'll see we have that inverse of the remaining ligament to the gamma exponent. All of that is over K mat, the material toughness. And in my case, I use the Wallen-J lower bound K mat that you'll find in API 579 or perhaps some other industry documentation. Now, there is a reason that I'm using lower bound Wallen-J. I've explained that in one of my other videos, a video called Pipeline Integrity, Things That Make Me Go, number 4. And that's a pretty important thing to use that K-mat. I don't want to mess around with other K-mats or the whole model goes sideways. And then for our load ratio, we'll take the failure strength, either predicted or actual failure strength, divided by the flow strength. And then again, we have that inverse of the remaining ligament ratio to the power of the gamma exponent. So I'm not actually going to bore you with all the mathematics. The derivation of the original log secant model and failure assessment diagram is available in various pieces of literature. So what I'm going to do is I'm just going to let you know this is how I've defined my KG and this is how I've defined my SG. And when I go through all that real math, I end up landing on exactly the same spot that the original failure assessment diagram lands on. So my K limit here, there is no change from the usual. And that's kind of a good thing and a bad thing. The bad thing is it kind of seems a little bit surprising because there's an 8 factor in there, and some of you might be expecting me to have a 10 factor because of my various changes in the gem. But the way the math plays out is I've got the correction factor buried in the kg term, and everything plays out really nicely. Now, the good thing is that the fact that I am landing in exactly the same place as the original failure assessment diagram gives me a lot of confidence that the basic form of the gem model is actually in very, very good shape. So let's take a look at what that gem limit actually looks like. So here we go. On the y-axis, we've got the fracture ratio, kg, which I defined earlier. On the x-axis, I've got the load ratio, SG, which I defined earlier. And that green dashed line represents the critical limit for failure. So if we have a data point which plots lower and to the left of that dashed line, officially that means that flaw is going to be safe. If we have a flaw that plots above or to the right of that line, that means that we have an unsafe flaw that's predicted to fail. So let's see how that plays out if we use some real data. The industry failure data that I'm using here is the original Battelle data that was used by the NG18 committee back in the early 1970s in order to validate their original log secant model. And you'll find that paper is Failure Stress Levels of Flaws in Pressurized Cylinders. It's an ASDM paper from July of 1973. Now, in that paper, we have 48 data sets for surface breaking cracks. Unfortunately, the data sets are not complete. There are some data sets that are missing their toughness information, which is quite important to this. What I've done here is I've decided to default to a Sharpie toughness of 34 joules, full size, which is the equivalent to 25 foot-pounds. And 25 foot-pounds toughness is provided as a pretty reasonable guideline for the fracture toughness of pipeline steels. And that was actually recommended in a paper by Kiefner in 2004, a paper that was written for PHMSA. So I'm going to use that. It doesn't seem to affect the statistics too much, so I hope that you're okay with that assumption. Now here I've taken those 48 data sets. I've gone through the exercise of calculating the fracture ratio kg. I've gone through the exercise of also calculating the load ratio SG. And then I've plotted all of those data points on my EGAD, my exponential gamma assessment diagram. So you'll see that some of my data points are in the safe zone and some of my data points are in the unsafe zone. And they seem to be approximately centered a little bit outside and a little bit inside. So that gives me some reasonable confidence that my numbers are pretty much in the right place. Now, the benefit of having an assessment diagram for your pipeline integrity work is that you can do predictions. So what I did is for each one of my 48 data sets, I actually used the goal seek within the Excel spreadsheet to figure out for each one of these data sets what combination of parameters would put me exactly on that critical EGAD K-limit. And if I do that, then I essentially come up with a predicted failure strength. If I then take the EGAD predicted failure strength and I map it against the true measured failure strength, I can get a sense of how well the model is validating. So I'm going to do that next. Okay, so here we have a standard validation plot. On the y-axis, I have the predicted failure strength. And so that's predicted using the method I just demonstrated, where I take a look at that EGAD limit, and I use numerical methods or the goal solver within Excel to calculate what strength would put those data points exactly on the critical line. Then you'll see on the x-axis I have the true failure strength, so that was measured in the laboratory by Battelle, and I've simply compared the two. Now, if this model were exactly perfect, you would expect everything to lie along the gray dashed line that goes right through the diagonal of this plot. That represents an exact perfect 1-to-1 ratio. Now, we don't actually have that. We have a few data points that are above and to the left of the line, and these represent non-conservative data points. So these would represent unsafe predictions for the pipeline. But we also have an equal number, or approximately equal number, of data points that are below and to the right of the line. These represent overly conservative predictions, which means that we would be safe in managing our pipeline, but there are some situations where we might be spending a little bit of extra money that we don't necessarily need to spend. Now you'll see if I put a trend line through there, I land on a slope of 0.99x. So that means that the agreement is very, very good. It's about, on average, about 1% overly conservative. Now, the fact that this lies so close to 1 gives me a lot of confidence that the model is mathematically correct. It's giving me very, very good predictions. There's a little bit of scatter, but that's nothing that's unexpected due to the nature of fraction mechanics being a statistical game that we're playing. So when I look at that, I've got an enormous amount of confidence, not just that the EGAD model is working well, but this really reinforces my confidence in my original GEM model. So I'm in a pretty happy place right now. I think that either one of the models, GEM or the EGAD, are somewhat interchangeable because they're built on the same foundational mathematics. I'll say that the basic GEM model is quite a bit more convenient to use simply because it's a one-line equation. You don't have to worry about calculating a separate Kg or a separate Sg, and you don't have to worry about using numerical methods to solve for your failure strength. But that's up to you. Some people have got different preferences. So if you're interested in pipeline integrity and the types of fraction mechanics models that I'm developing, I'd like to encourage you to see some of my other videos. I have a 6-part series called Pipeline Integrity, Things That Make Me Go, And that's really a critique of some original work that was done back by the Battelle Institute almost 50 years ago. There are some, I think, some logical errors in there that really should be investigated in a lot more detail by the pipeline industry. Fixing some of those errors has given me some good validation from the GEM model and now the EGAD model. And I encourage discussion on the various topics I bring up there. I also have a 6-part series, Pipeline Integrity Gamma Exponent Model Validation. That's where I look at 5 different flaw types and show how they all validate quite well to the original gamma exponent model. And I can actually take all 5 data sets that I've got from the different flaw types, pool them together, and get a mega validation in part 6, which shows that the overall mathematics of the model is doing quite well for itself. I have pipeline integrity, stress corrosion, cracking, shielding factors. That's where I demonstrate how I've come up with a depth correction factor to account for shielding of SCC colonies. And I have pipeline integrity model selection statistics, which is a demonstration of why accuracy and precision of these fraction mechanics models is so important, not just for safety of the line, but also running a pipeline integrity program in a very, very financially responsible and efficient manner. So I encourage you to look at those. Those are, of course, all free. Each one of those videos is between about 10 minutes or 20 minutes. If you're more interested in reading serious technical papers, I do have 3 real publications. One of them is through NACE. I put together a validation effort for the metal loss or the corrosion flaws for a conference back in February of 2020. I have some crack validation work that was put together for an ASME pressure vessels and piping conference. That's the virtual conference. And then I also have the formal mathematical derivation of the GEM model has been published by ASME Journal of Pressure Vessel Technology. So please help yourself to that if you're a math nerd that would like to get a little bit more information on how the GEM has been originally derived. If you've made it this far, thank you very much for your time. I appreciate it. If anybody has any questions about what I've done, please feel free to contact me through LinkedIn. Or if you watch some of my other videos, you probably get a much better sense of where my head is at and how I've come up with the various mathematical forms of equations that I have. So until next time, thank you very much for your time. Bye.